Hello, in this video I want to look at parametric equations and circles. So normally what you would start with is an equation with x squared plus y squared equals to r squared. If, for example, the center is not the origin, then that can be easily accounted for. Now, if we were going to parameterize this equation, then really what's fundamental is the trigonometric identity cosine squared plus sine squared. And just like with the parameterization of the ellipse, it's actually the same concept. The only difference is that the radius is 1 or that the A and the B are both the same, meaning that the focus is right at the center. So in particular, if we wanted to be able to find, for example, how we can get the equations, we work our way backwards where we divide by r squared. Or another way to do it is just to know that, okay, fine, if you know that cosine squared theta plus sine squared theta equals to 1, then yeah, we can kind of work our way backwards, either or. So suppose that you did take the equation x squared plus y squared equals r squared. And after that, let's say that you did divide by r squared, and you know that that's going to be x over r, and that's going to be squared. And then you have that that's going to be y over r, and that's going to be squared as well. But looking at this, see like how the fundamental identity says that cosine theta is squared and sine theta is also squared. So traditionally, we have that the definition of cosine of theta is equal to x over r. So in that sense, you already have what cosine theta would have to be equal to. That it would have to be that you have cosine theta is x over r, which means that the x of t is, for example, r times cosine of t. Similarly, if you say that the function sine theta is equal to y over r, then in that case, that's going to give you that the equation for y of t would have to be r sine of t. Now, of course, the parameter of interest is t usually, because it's some type of interval with respect to time, mostly. So even if we use theta, t, r, s, it's really all the same. And in any case, we have that this would indicate that the starting point, if t was a parameter from 0 to 2 pi, would be at one of the vertices, which in this case would be r comma 0. But as you increase theta, that means that it's moving in a counterclockwise motion. But notice this, because cosine is squared, that means that it could have been negative, and then the sine squared is also a squared term, so that means that it can also be defined as negative. But notice this too, that we could technically interchange the cosine theta and the sine theta, and would it change anything about the shape of the graph? And the answer to that would be no, it wouldn't actually. It would just change the orientation of which that the particle moves from 0 to 2 pi radians in any case. So let's say, for example, that you have an equation of a circle, and that equation of a circle is given by x squared plus y squared equals to, let's say, 9. So with that, we can see that the radius of this equation is that r equals to 3. So that means that the equations, as it relates to this particular circle with radius 3, that it would have to be that x of t is equal to 3 cosine of t, and that y is equal to, not y, but y of t, right? So y of t would have to be 3 sine of t. But all of this would be conditional to that the t would have to be from 0 to, not 360, but 2 pi radians. Now, if you wanted to actually talk about, like, let's say, for example, the speed of which that the rotation occurs, then that has to deal with the angular velocity of the motion from going from start to finish. Or if you think about it like this, when you're looking at your trigonometric functions in terms of like their graphs, you saw that the period was always from 0 to 2 pi, but what if the coefficient was like, let's say, y equals cosine 2x? Then you know that that time interval is actually a lot faster, actually. But then if you have that the coefficient is very small, then it's actually extended. So that means that you could actually change this time interval to whatever you want it to be. But then what's going to happen is that it's either going to speed up the process of which that the rotation occurs, or it's going to decrease it or slow it down. So the compression is actually speeding it up versus the stretching is slowing it down in actuality. And here I'll just show you like a tiny little demonstration of when the r is equal to 3, and the parameterization, as we mentioned, is r cosine a, well, theta, right, or t, and then you have r sine a. Now look at this. We're going to go from 0 to 2 pi, right? So here, this is going to rotate 360 degrees. So see like how it started at 3, 0, and as we rotated, you see that now it's at the pole at 90 degrees. And then you have that 180. It's at the other vertex. It's not going to be exact, right? But it definitely does pass through there. And then it hits the other side, 0, -4. I'm sorry, 0, -3. And then you rotate again, and there it goes. It finished, right? Or just press play, and you see that it's rotating. Okay, so it's coming back around, and now it's going in a counterclockwise motion, and you see like how it's rotating in that sense. Now, one thing that could be useful about this is that what if you were looking at the orbit of a satellite, for example? That could be modeled because we have that our planet is surrounded by tons of satellites in actuality, of which surprisingly many of them may actually be inactive in some cases. But either way, we could possibly model a type of satellite and its orbit. Or, for example, what if it was a ship? Then in that case, we could do that too, as long as it's something of which that is within our atmosphere, if you will. And in any case, we're just trying to calculate some type of specific, you know, navigation or entry for that matter. But look at this though, like if I were to make the radius equal to 1, now I'm defining actually what you know as the unit circle. Of course, if I just need to zoom in, I can do that, and I can just press play. And you see like how it's giving you all of the values in terms of the x component, the y component, with regards to the trigonometric function cosine and sine respectively. And note that you could find tangent, right? Because tangent is just merely y over x, which that you already have according to this diagram. And then look at this though, like if I did go back to my original question, how r equals to 3, and let me just zoom out just a tiny bit, and see like how over here, if I was going to change the orientation in a sense that I change the x component, y component, like whether it's going to be positive or negative, see what happens. that, let me see, let's go back to the 0. The new starting point is a little different. Ignore this line because it's programmed in such a way that it was with regards to that specific parameterization. But you see like how the starting point actually did change now. And then notice this though, like what if we made this negative? But as I increase the radian measure, see like how now it's moving in a different direction actually. It's moving in a clockwise motion, but it's still terminating at the same starting point, okay? And see like how if we were to switch these two, well, to switch the two trigonometric functions, would it really change anything about the shape of the graph? And the answer is no, it wouldn't. So here we have that in this particular case, it starts at the top of the pole now. And see like how, you know, if we were to, let's say, for example, make it negative, so like if we have that this one would be negative, now it's at the bottom. Okay, so we have that, you know, with respect to parameterizing a circle, then it really is fundamental to using the specific trigonometric identity cosine squared theta plus sine squared theta equals to 1. But that means that in actuality, as it relates to things beyond this, such as like, for example, like a hyperbola, then we won't be able to technically use that one. You know, what I mean by that is we wouldn't be able to use the trigonometric identity cosine squared theta plus sine squared theta for that one as in actuality. However, if we were to use the other identities in terms of like tangent, secant, cotangent, cosecant, then that could be a possibility in actuality for the parameterization of those equations. But for this one, you know, for ellipses and circles, they're usually pretty simple in that we just have to use the fundamental identity that most people can work with in terms of like, you know, oh, okay, it's really just sine squared plus cosine squared. And the only thing that I have to take in mind is the starting point and then the circular motion, like whether it's going to be counterclockwise or clockwise.